Okay. Hello everyone, welcome back to Imperial Coaching Center, and today we'll be discussing the questions of ANNTS 2024 Physics. Okay, and here's your first question. So the first question is, a diver underwater looks obliquely at a fisherman standing on the bank of a lake. The fisherman looks shorter to the diver than what he actually is. Well, the statement is false. Let's understand it making a diagram. Okay, let's see. Okay. So this is my rarer medium. Here I have the fisherman, let's say. This is the height of the fisherman. Okay, and this is my denser medium, water. Okay, here I have the diver somewhere here, let's say. The diver is watching the fisherman from here. Okay, chalo. Now what is happening? Let's say, let's pick two rays. Okay, this is my first ray from the head of the fisherman, and this is my second ray from the head of the fisherman. Now try to understand one thing. The ray will be traveling from rarer to denser medium. Okay, if I make a normal here, what will happen? The ray will slightly bend towards the normal. Okay, towards the normal. Here, if I'm going to make a normal here, this ray, see the initial path would have been this, okay, na? But what is happening? It will bend towards the normal. It will bend towards the normal. Now, okay. Now, if you project this rays backward, okay, if you project this rays backward, this will meet somewhere here. So you can see the height of the fisherman has changed. It has increased actually. So the first statement is false. The first statement is false. And the second statement is, a convex mirror always produces a virtual image independent of location of real object. Of course, see, when you talk about convex mirror, okay, if you are talking about convex mirror, then the image formed is always virtual and erect. Okay, so your answer is option number 3. A is false and B is true. So this is the answer for the first question. Let's see what is the second question here. Okay. The second question is, a short bar magnet has a magnetic moment of 0.48 joule per Tesla. The magnetic field at 10 centimeter distance from center of magnet on its axial line is. Okay. So here the magnetic moment is given to us. The magnetic moment is 0.48 joule per Tesla. 0.48 joule per Tesla, and we need the magnetic field at a distance of 10 centimeter. So distance is given as 10 centimeter. In terms of meter, it will be 0.1 meter. 0.1 meter. And we need the magnetic field on the axis. Okay. B on the axis will be mu naught by 4 pi, 2 times of m divided by d cube. Now, if you are going to place this value, say in place of mu naught by 4 pi, we can simply put what? 10 to the power minus 7 multiplied to 2, and the magnetic moment is given as 0.48 divided by d cube, that means 0.1 whole cube. Okay, your answer will be 0.96 into 10 to the power minus 4 Tesla. Okay, now 10 to the power minus 4 Tesla is nothing but Gauss, 0.96 Gauss. Okay, so now try to understand one thing. So the answer is 0.96 Gauss along south-north direction. Okay, now if the magnetic field, if you are supposed to find out the magnetic field at the equator, then just divide this value by 2. Okay, the answer will be 0.48 Gauss in the north-south direction. Alright, let's move to the third question. What is the third question? The refractive index of glass is 1.5 and the speed of light in glass is, okay, so we need the speed of light in glass. Refractive index of glass is given. That means mu is given to us. Mu g is given as 1.5. Speed in vacuum is given. That means c is given to us 3 into 10 to the power 8 meter per second, and we need the velocity, the speed of light in glass. Velocity in glass. Okay. Now, how will you find out? See, we know mu is equal to c by v. All right. So from here, can I write this V as Vg? So Vg will be, speed in glass will be equal to C by mu. What is C? Speed of light, 3 into 10 to the power 8 divided by mu, refractive index 1.5. So this is equal to 2 into 10 to the power 8 meter per second. So the velocity in glass is 2 into 10 to the power 8 meter per second. That means option number 2 is your correct answer. Option 2 is your correct answer. Okay, now let's move to question number 4. Question number 4. Sorry. Okay. The distance for which ray opticals is a good approximation for an aperture of 4 mm and 400 nanometer wavelength is. Alright, so aperture A is given as 4 mm. In terms of meter, it will be 4 into 10 to the power minus 3 meter, and wavelength lambda is given as how much? 400 nanometer. That means in terms of meter, 400 into 10 to the power minus 9 meter, right? So we need the distance, isn't it? Distance is equal to a square by lambda. That means 4 into 10 to the power minus 3 whole square divided by 400 into 10 to the power minus 9. So further we can write it as 4 multiplied to 10 to the power minus 6 divided by 4 into 10 to the power minus 7, right? Minus 7. So this 4 times, and here it will be how much? 10, isn't it? Okay, so 4 into 10 will be 40 meter. And your answer is option number C. Answer is option number C, 40 meter. Let's move to the next question. Alright, the next question is in photoelectric effect experiment. The intensity of light is varied by changing the distance of light source from emitter. Which of the following graphs depict the variation of photoelectric current C with intensity of light? Okay, the answer is option number 1 here. The answer is option 1. Why option number 1? Because intensity is directly proportional to the current. Okay, so it's linearly dependent on it. Hence, option 1 is your correct answer. Let's move to the next question. The next question is, a moving electron has a wavelength of 1 nanometer. The kinetic energy of electron is, okay. Wavelength is given here. Wavelength is given here as 1 nanometer. 1 nanometer. That means 10 to the power minus 9 meter. 10 to the power minus 9 meter. We need to find out the kinetic energy of electron. Kinetic energy of electron. So here we can use this de Broglie's wavelength. De Broglie's wavelength. Okay. So we have lambda is equal to h by p. What was h? H is the Planck's constant, right? H is the Planck's constant, and p is momentum. So from here I can write it in this way. Lambda is equal to h by mv, right? H by mv. Okay, so since we need kinetic energy, so we'll be modifying this equation a little bit. What we'll be doing, we'll be squaring this formula on both the sides. Okay, so we can write here lambda square is equal to h square by m square v square. M square v square can be written in this way as well, no? mv square. I'm just taking mv square together. Okay, there's a reason. See, kinetic energy is what? Half mv square, isn't it? So mv square can be written as 2 times of k. K is the kinetic energy here. Okay, I'm going to replace mv square with k. Okay, so instead of writing this, lambda square is equal to h square by m. In place of mv square, I can write here 2 times of k. So we need k. I'm taking the k. I'm transposing the k to the left hand side. So k will be equal to h square by 2m lambda square. So we have an expression to find out the kinetic energy of the electron, right? Okay, so kinetic energy K is equal to H. Planck's constant is 6.6 into 10 to the power minus 34 joule second, right? Divided by 2. Then we have the mass, right? Mass of what? Mass of an electron. Mass of an electron is 9.1 into 10 to the power minus 31 multiplied to lambda square. Lambda is given as 1 nanometer, that is 10 to the power minus 9 whole square. 10 to the power minus 9 multiplied to 10 to the power minus 9. If you're going to do all this calculation, you'll be getting the answer as 2.42 into 10 to the power minus 19 joule. 2.42 into 10 to the power minus 19 joule. And since the answer is given in electron volt, what we'll be doing, we'll be dividing this value with 1.6 into 10 to the power minus 19. Okay, then you'll be getting the answer approximately as 1.5 electron volt, that is almost equal to 1.44 electron volt. So your answer is 1.44 electron volt. Option 2 is the correct answer. Option 2 is the correct answer. Let's move to question number 7 then. Question number 7. Okay, this is an assertion and reason based question. What is given to us? The Bohr's model is not applicable to atoms having many electrons. Okay, of course, the Bohr's model is only applicable to single electron species. See, single electron species means single electron species. When I'm saying single electron species, try to understand one thing here. We are talking about hydrogen-like atom. Hydrogen-like atom. Atoms with single atom. Okay. Example, hydrogen itself. Helium positive, He plus. Okay. He plus has got only one electron. Then we can take Li plus plus. Okay. Li plus plus will also have one electron. Beryllium plus plus plus, etc. Okay, so this is applicable to single electron species. Okay, and the reason is in atoms having many electrons, each electron interacts not only with positively charged nucleus but also with all other electrons. See, in single electron species, what is happening? One electron is interacting with the nucleus, right? But in multi-electron species, what happens? The electron not only interacts with the nucleus but also it interacts with the neighboring electrons. All right, that is the reason why Bohr's model only talks about single electron species. Okay, so here both the assertion and reason are correct. Both assertion and reason are true, and the reason is correct explanation of the assertion. Option number 1 is correct here. Option number 1. Okay, let's move to the next question. Question number 8. The correct statement of the following about electromagnetic waves are: accelerated charges radiate electromagnetic waves. The frequency of wave is equal to the frequency of oscillating change. Gamma rays are produced by radioactive decay of nucleus. Well, all the three are correct. All A, B, C are correct. In the next question we have, a 10.2 electron volt electron beam is used to bombard gaseous hydrogen at room temperature. The series of wavelength that will be emitted is, okay, try to understand here. When we talk about the first orbit, when we are talking about the first orbit, okay, first orbit, we know an electron will be having minus 13.6 electron volt. Okay, when we are talking about the second orbit, an electron will possess minus 3.4 electron volt energy. Now, to make this transition from ground state to excited state, it will have to absorb 10.2 electron volt energy. Only then it can jump from the ground state to excited state. Now, what happens, you see, if this electron has to come back from the excited state to the ground state, it will have to emit that much of energy that it has absorbed while moving from ground state to the excited state. So what is the amount of energy? The amount of energy is 10.2 electron volt. Now try to understand one thing. The transition is happening from n equal to 2 to n equal to 1, from the second orbit to the first orbit. And this transition is nothing but Lyman transition or Lyman series. Okay, the series of wavelength that will be emitted is Lyman. Alright, okay, let's move to the next question. What is the ratio of the radii of the nuclei of mass number 27 and 64? Okay, let's do this. So we have this equation. We know that radius of the nucleus R is given as R naught A to the power 1 by 3, right? And A is what? A is the mass number. A is the mass number and R naught is 1.2 Fermi or 1.2 into 10 to the power minus 15 meter. We don't need to replace the values here, of course. Okay, we can cancel out. So for the first nuclei, let's write R1 is equal to R naught A to the power 1 by 3. Can I write it as 27 to the power 1 by 3? Let this be equation number 1. And R2 at the same time will be R naught 64 to the power 1 by 3. Equation number 2. Now if I'm going to divide this R1 by R2, so you see 27 1 by 3, R naught 64 to the power 1 by 3. R naught and R naught can be cancelled here. You'll be left with, okay, 3 cube means 27, right? So can I write it in this way? 3 cube means 27, 4 cube means 64, right? 3 by 4 whole cube, and we have a 1 by 3. So this 3 and this 3 is getting cancelled. You'll be left with 3 by 4. That means what? 3 is to 4. And your answer is option number 1. 3 by 4. 3 by 4. Okay. Alright. So these are the questions from ANNTS 2024 Physics. Alright. We'll be making another video on the next consecutive questions. Thank you so much. All the very best.